Alright, so we're still working in 2.6 on related rates. And we are going to pick up on example 3, continuing from our last video. And example 3, we're going to say air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. We need to find the rate of change of the radius when the radius is 2 feet. So, when I am writing the things that I know and need to find, I'm going to start by what we're given. So my given rate we know that dV, the change of volume over time, dV dt, is 4.5 feet per minute. We need to find dr dt, change of the radius over time, when our radius is 2 feet. Now, this is a balloon, and we're talking about, and it's spherical, in fact, the volume changing when we're talking cubic feet. So, we need to know what's the volume, the equation for a volume of a sphere. That equation, which we should have learned in geometry, but not a big deal if you didn't, I'm going to give it to you. It's written as V equals 4/3 pi r cubed. So now what we're going to do is we're going to implicitly differentiate this on both sides with respect to t. So we're going to take the derivative of the volume, so we're going to write dV dt, which we've got. It's just going to be that. It's going to equal dr dt, and then we're going to take the derivative of 4/3 pi r cubed with respect to r. So we're going to bring the 3 down. In fact, I'm just going to do that up here in the corner. 4/3 pi r cubed. When we take the derivative, we bring the 3 down. 3 times 4/3 pi r squared, and these 3's are going to cancel out. So we're going to be left with 4 pi r squared. Now there's some things we know. We know dV dt, and we know r. So let's put those into our equation. dV dt is 4.5 equals, we don't know dr dt, 4 pi dr dt times 4 pi times 2 squared. Well, 2 squared is 4, and 4 times 4 is 16. So we got 4.5 is equal to dr dt of 16 pi. Well, we want to solve for dr dt, so we're going to take 4.5 and divide it by 16 pi. In fact, we're doing that on both sides. Now, if we just take a calculator and put 4.5 divided by 16 pi into it, we're going to find that dr dt is about 0.09 feet per minute, which is what we were asked to find. So let's look at another example of how this related rates stuff works. In this example, example 4, we're going to look at an airplane. It's flying on a flight path that will take it directly over a radar tracking station at an altitude. In fact, let me rephrase that. The airplane's altitude is 6 miles the distance, s, is decreasing at a rate of 400 miles per hour when s is equal to 10 miles. We need to know what is the speed of the plane. Now I don't really know what formula we would use for this, so I am going to actually start this one by making a bit of a diagram. So I'm going to write ST for the station, the radar station, and I'm going to write AP for the airplane. What I know is that the airplane is not quite over that station yet, but it is moving towards the station, and that there's an altitude that airplane is traveling at that is 6 miles above. Now, I don't know how far exactly horizontally the airplane is yet, so we're going to call that X. What we do know is the direct distance from the plane to the station. Here, that is represented by S. So now I'm going to start writing some stuff that I know and don't know about this equation. What I know is that my given rate it's given by ds dt, the change of the distance from the airplane to the station over time, is equal to negative 400, because it's decreasing, miles per hour when the distance is 10 miles. What we need to find is the change in horizontal distance over time, because that's going to help us figure out the speed. Horizontal distance over time gives us speed when s is 10 miles. But we also need to figure out an x value. So one way we can figure that x value out is if we notice in this little triangle we made, we've got a right triangle. We know the altitude is always 6, and we know an s value of 10. So why don't we use the Pythagorean theorem to find x? So we know one of the legs, and we know the hypotenuse. So to figure out x, we can take the square root of our hypotenuse squared, which is 10 squared, and subtract 6 squared from it. That's going to give us the square root of 64, which is just going to be 8. So we need to find dx dt when s is 10 and when x is 8. And both of those are in miles. Now, we're going to just use the Pythagorean theorem for our equation. What we know is we've got x squared plus 6 squared equals s squared. So now let's differentiate each side with respect to t. So we're going to have dx dt times 2x, because the derivative of x squared then would be 2x. The derivative of 6 squared, that's 0, so we can ignore that. That's going to equal ds dt times 2s, and we want to find dx dt. So let's put the information we know in here. We know ds dt is negative 400 and s is 10. So we're going to have 2 times 10. And we also know that x is 8. So we're going to have 2 times 8 times dx dt. Well, negative 400 times 2 times 10, that's going to give us negative 8,000. And 2 times 8 is 16. So we've got dx dt times 16. But we're going to want to divide the negative 8,000 by 16. That's an equal sign after my 16 I wrote down there. So once we do that, and go ahead, use a calculator to do it, we're going to find that we're going to get negative 500, but we can't really have negative speed. So what we can just say is the speed is 500 miles per hour. Because even if we were driving in reverse, our speed's not going to be negative. And even though in the last video I said we're going to do 3 examples in here, I think we're actually going to call it quits, and this can be the end of our related rates lesson.